Okay, so in the last podcast, we looked at some early cosmological models and we looked at the cosmology as described by Newton and saw a couple of problems with it. Um, and so today, what we're going to do is look at further developments and solutions to that problem. Well, Einstein, just under 100 years ago, in 1917, Einstein produced a description of the universe and the shape of space based on his special and general theories of relativity. His general theory of relativity specified that space-time must be curved as an explanation for gravity, amongst other things. That described local distortions, but he did wonder about the shape of the universe as a whole. It was known by then, by 1917, that stars are pretty much things like our sun that are very far away. We knew that by looking at their spectra. What we didn't know about at the time was things like what are galaxies. We knew they're faint patches of light, but are they things that are inside our own galaxy? Was there such a thing as a galaxy, or was there things like galaxies as we now understand them? Einstein realized that his equations led to a few uncertainties, and he invented a term called the cosmological constant, which he needed to do to keep the universe static to oppose to gravity. And he later said this was his greatest mistake. But was he? Friedman was a Soviet scientist, Russian and then Soviet, who developed Einstein's equations and very much, he developed versions of equations for all sorts of universes, but he very much supported the idea that Einstein's equations described an expanding universe. And a great unsung hero, Lemaitre, a famous Belgian scientist, who was also a Catholic priest, developed those equations even further and used to apply them to astrophysical models. And in fact, he predated a lot of work the next guy we're going to look at did, but because he was publishing in obscure European journal, he didn't quite get the recognition that he deserved. But cosmologists today know the name of Lemaitre. So who am I talking about? Well, I'm talking about Mr. Edwin Hubble. Now, Edwin Hubble was a great American astronomer of the earlier 20th century, and he was the person who conclusively demonstrated the existence of galaxies apart from our own. He did that by taking the Cepheid variable relationships, which were developed particularly by Henrietta Leavitt 30 years earlier. And so he knew, and from this data, he knew that the distances to galaxies, relatively nearby galaxies, but he knew their distances. And he also took some earlier observations by the astronomer Slipher and combined those two things to basically produce a graph. And the graph that he produced gave him a relationship, which you can see here. The graph he produced was one that had a direct correspondence between the distance to a galaxy, as shown here, and its velocity moving away from us, using Slipher's redshift data. He came up with two conclusions. One, all objects in deep space, greater than 10 megapascals away, have a Doppler shift interpreted as a radial velocity away from the Earth. Okay, so in other words, it doesn't apply so much to the close by galaxies because they're close by, because gravity is, as a percentage, a much more dominant effect. But yes, they're all moving away from Earth, and that velocity is proportional to their distance away from Earth. So there's a straight line graph, he's basically saying, if you plot distance against recessional velocity. And the equation for that, therefore, is a very simple V equals HO, or H0D, where H is the Hubble constant. It's the gradient of that line. Determining that gradient was surprisingly difficult. In 2001, the Hubble Space Telescope team put together all of the different sources of data that they could find and obtained a value of 72, kilometers per second per megapascal, with a rather still rather a large odd margin of error, 72 plus minus 7, so almost 10%. In the last 10 years or so, though, some new satellites using different techniques have come up with much better techniques, and the Planck mission launched in 2013, its best estimate is 67.8 plus minus 0.77. So still, you know, a 1% or more error, but better than 10%. The key thing to take away from this is that if we live in an expanding universe, that means that tomorrow will be bigger than it is today. Yet that also means that yesterday it was smaller than it is today. And if we trace that back, then presumably at some point in the past it grew from a singularity, a point of infinite density. This resolves Olbers' paradox. It resolves Newton's problems, because Olbers' paradox relied on a universe that was infinite, infinite in age and infinite in extent. And the observable universe, the universe that we can see, is neither infinite in size or age. So Olbers' paradox is no longer valid. Every line of sight will not necessarily end upon a star. In fact, it doesn't. It's important to note that although we always observe everything moving away from us, that doesn't mean that we're in the center anyway. Any raisin in this raisin bread would observe exactly the same thing. Interestingly, we can also use Hubble's constant and turn it around to calculate the age of the universe. And if we take the latest values and turn it around, we get a value of 4.455 times 10 to the 17 seconds, which is 14.4 billion years. That's not actually correct because the graph is not actually linear, but it does give you a good order of margin estimate. The current best estimate of the age of the universe is about 13.77 billion years. Okay, so you're slightly overestimating by doing 1 over h0, which is in the data booklet, you need to know it. But not by too much, I guess. Okay, so we've described the Big Bang model, starts at a point and expands. We've shown Hubble's law, which is given down here, plus the time approximately equals 1 over HO. Both space and time originated with the Big Bang. From this model, it's stupid to say before the Big Bang because there was no time before the Big Bang. And you can now solve some problems involving Hubble's law, and you estimate the age of the universe. Thank you very much.